Hi, I'm Rob, and I'd like to welcome you to this video on prompt engineering. In the previous videos in the playlist, we saw how large language models work, and then we built an LLM-powered application using React and FastAPI. In this video, we'll focus on one of the most misunderstood parts of building LLM systems, prompt engineering. Prompt engineering isn't about finding the right magic words. In real systems, prompts act as runtime configuration for probabilistic software. I'll show you how engineers should actually think about prompt engineering, including structure, constraints, message roles, structured output, validation, and more. Now, let's jump into Jupyter Notebook and get started. Now, before we look at the first notebook, I want to call your attention to the README, where you'll find the steps to create and activate a virtual environment, install the dependencies, and launch the notebooks. And I also want to point out that you'll need an OpenAI API key since the demos will be using GPT-4o Mini. So I'll start by launching a terminal and changing into the project directory. Then if this was my first time creating a project and the virtual environment didn't exist, I'd run this command. But as you can see here, I already have my VM configured. So I'll skip that and just activate the environment. Then I already ran pip install, but let's take a look at the requirements file to see the libraries needed for the notebooks. And I already copied the env example, but we'll take a look at that as well. And here you see where you'll need to put your OpenAI API key. Now, scrolling down to the notebook section, you'll find a description of the content in the notebooks, which are all in the demo folder, but we'll be diving into them in a second. So I'll scroll down and grab the command to finally launch the notebooks, jump back into the terminal and execute it. And here we see the first notebook. As previously mentioned, we're using the OpenAI client with the GPT-4o Mini model, and we put the API key in the .env file. So I'll go ahead and run the setup cell to load the key from the .env, create a variable to hold an instance of the OpenAI client, and set our model to GPT-4o Mini. Now I'll scroll down to the first section on reframing prompt engineering. Now most people treat prompt engineering as finding the right magic words. The better way to think about it is that the prompts are runtime configuration for a probabilistic system like function parameters or a config file. You're not asking questions, you're specifying behavior. The same prompt text can behave very differently depending on parameters like temperature, which I'll show in the code. Here, we'll use the exact same prompt, list 3 outdoor activities. But first with a temperature set to 0 for a deterministic output, and then at 1.5 for a more creative output. And as we can see here, the prompt didn't change, the configuration did. That's why this is engineering, not wordsmithing. Now let's look at message roles and instruction hierarchy. The OpenAI Chat Completions API gives you 2 roles for your messages, system and user. The system message is where you put behavior and rules, and also application context like this user is a premium member. The model treats system as a higher priority than user, so you can lock down behavior. Let's look at that in the demo. First, in the message, we'll add a role of user, and the content will be the question, what's the weather like, with no system message. And we'll run this, and you get a normal sounding answer. Now we'll add a system message that says to always respond in pirate speak. So it's the same question, and we'll run this. And although it's the same user question, we get a completely different answer. The system message controls the personality and the behavior without changing what the user said. Now here we'll create a conflict. The system directs the model to always respond in exactly 1 sentence, be extremely concise. Whereas the user says, explain photosynthesis in great detail with multiple paragraphs. So let's go ahead and run this. And we see the system message wins. That's how you lock down behavior even when the user tries to override it. So you'll often have application context in the system message, such as user tier, permissions, region, that the model should use, but the user shouldn't see in the prompt. Here in the system role content message, we're telling the model to act as a support assistant and that the user is a premium member, so the model can then offer priority support without putting that in the user message. So let's go ahead and run this. And we see in the model's response that it's recognized the user as a premium member and that it can assist the user with priority support. Now let's take a look at how we can use message roles strategically. You should use the system role for non-negotiable behavior and application context, and the user role for what the user actually wants. This final example is a support bot with clear rules in the system message specifying no pricing and no promises about timelines, as well as the user's account status. So let's run this. And we see in the response that even though the user asked for a discount and a launch date, the model stayed within the system role guardrails. This diagram shows that model behaviors come from the combination of system instructions, user input, and parameters like temperature. The prompt text alone isn't the behavior, it's part of a larger runtime configuration. Now let's jump into the next notebook and look at prompt structures and constraints. First I'll run the setup cell, then scroll down to the first demo. So when it comes to writing prompts, hard coding a prompt like write a product description for a blue backpack has obvious problems. You can't reuse it for other products, you can't control tone or length, and you're mixing data with instructions. Here, this code shows that anti-pattern where the function has the prompt baked in. If we run it, we get one kind of output, but we can't reuse it or test it meaningfully. A solution to that problem is to use parameterized prompt templates, where prompts should be functions, not strings. Here we've defined a function that takes a product name, color, list of features, sets a tone, and the max words. Then it builds the system and user messages from those parameters. So we can use the same logic with different inputs, which keeps data separate from instructions and makes it reusable and testable. So first I'll run the function with a professional tone, and then with a casual tone, and we see the differences. When it comes to prompt composition, you can go further than just defining prompts as functions and build prompts from reusable building blocks, which use dictionaries for tone and format, then a function that composes them. That way you can mix and match the tone and format without rewriting the whole prompt. So this code composes a technical bullet point prompt, which we can see in the output when we run the cell. Prompt constraints can be soft or hard. Soft is like, try to keep it brief. Hard means making the rule explicit and non-negotiable with language like strict rule or exactly 2 sentences. We'll run both constraint types in the following cells. Here we have a soft constraint which asks for brief responses but doesn't enforce it. So when we run the cell, we see the word count is still fairly long. Now with a hard constraint, we'll add a strict rule which says respond in exactly 2 sentences, no more, no less. And when we run this, we see the model sticks to 2 sentences. So use language like strict rule, always, never, exactly, when you need the model to obey. As you probably know, hallucinations are when a language model confidently generates information that sounds plausible, but it's actually incorrect or made up. This happens because models are trained to be helpful and will sometimes fabricate details rather than admitting they don't know something. So to cut down on model hallucinations, you constrain the model to only use information you provide. Without that, if you ask about a product, the model might make up specs, as we see here. In this example, we're providing a short product context with product details and a strict rule instructing the model to only answer from this context. If something isn't there, say, I don't have that information. So let's run this cell. And we see the proper results for the product. And now we'll run an example where we'll ask a question that isn't in the context. And we see the model appropriately refuse to answer the question. When it comes to tone and style of the model's output, you can control this by passing in a list of rules, such as use numbered steps, technical language, and no marketing. If we run this, we see the response. Or we can do the opposite and set the style rules to use enthusiastic language, focus on benefits, not the technical details, and keep it simple and friendly. So let's run this, and we see the response. So we use the same underlying task, but with different styles, and we see the differences in the output. Now we'll tie all this together with a small prompt builder. Here, prompts are treated like functions, not strings. We separate data, constraints, and system rules, then compose them into system and user messages in a reusable way. Here, we'll create a prompt builder class. Then we'll set the role, add constraints, either strict or soft, optionally set the context, then build the system message, and execute. So for the example, we'll create the prompt using the prompt builder, setting the role as technical documentation writer. The constraint will be to use numbered steps, keep under 100 words, and include code examples where relevant. Then we'll execute, passing in the prompt of how do I create a virtual environment in Python. So let's go ahead and execute, and we see the results. Now let's jump into the next notebook and take a deep dive into structured outputs using JSON and Pydantic. On the left, free text output is hard to parse and easy to break. On the right, structured JSON output can be validated against the schema and safely used in code. If you ask the model to extract product name, price, and category and leave the response as free text, you get something that's hard to parse reliably. Formats change, there's no validation, and it could break downstream code. Here, we'll do one free-form text extraction so you could see the problem. Then we'll fix it with structure. OpenAI's response format lets you request JSON instead of plain text. We set response format to JSON object and ask for the same extraction. And when we run this, we see the model returns valid JSON, which we can parse with JSON loads. So we get a structure, but we still don't have a fixed schema, like field names and types can vary. So next, we'll add schema. Here, we define the exact JSON shape we want in the prompt: name, price, category, in stock, and the model follows it better. But we still don't get runtime type checking or constraints like price greater than 0. For that, we need Pydantic. Pydantic gives you a schema with types and constraints, like price has to be greater than 0, and name can't be empty. So we've defined a product model, which we can use to generate its JSON schema and pass that into the prompt. So let's go ahead and run this to create the class and the generated schema, which we can then pass into the prompt. So if we run this cell, we see we were able to parse the response to extract and validate the object and display its properties. Now, even with JSON mode and a schema in the prompt, the model can sometimes return invalid JSON or values that fail validation. So we need retries and fallbacks. First, we'll add retry logic, where we'll try a few times, and if validation or JSON parsing fails, we'll retry again before giving up. So here's our extract product with retry function, where it takes text and max retries for a product. We'll create the JSON schema, and then for each attempt in the max retries range, we'll try to call create on the chat completions API, passing it the model, the message, and the injected JSON schema. Then if we have a result, we'll pass it to JSON loads, create a product, and then return it. If there's a validation error and we're out of retries, we'll return none. And if there was an error parsing the JSON and we're out of retries, we'll return none as well. So let's go ahead and test this with valid input. And we see the data was successfully extracted. Now let's look at a fallback strategy. Where we've defined our function, we'll try calling extract product, passing it the text and returning it. If there was an exception, we'll return a default safe product. So let's go ahead and run this with some ambiguous text instead of a well-defined product, which we had before. And we get the ambiguous product. Now let's look at an example where we use Pydantic to handle nested data models. Here we've defined a class of review, which has properties for rating, comment, and reviewer, as well as a class for product with reviews, which has a product name, price, category, average rating, and reviews, which is a list of review objects. Here we have our extract product with reviews function, where we define the schema JSON, call the complete method on the chat completions API, passing the model, the message with the schema injected, and roles with response format set to JSON object. Then we'll create the text variable, passing in the product and the reviews, which will pass to the extract product with reviews function, ultimately getting our product back and printing the results. So let's go ahead and run this. And here we see the structured JSON object for the product with its price, category, and reviews, each of which has a rating, a comment, and a reviewer. All right, now it's time to bring all this together with an end-to-end example. This is a typical production extraction flow. Generate structured output, validate it, retry on failure, and fall back to a safe default instead of crashing your app. So in production, you want a clear result type, success with data, or a specific error and attempt count. In this example, we defined an extract result class with a status, data for an optional product, an optional error, and number of attempts. The status is an instance of an extraction status, which is an enum with various response types. The extract product production function tries up to max retries to call the create method on the chat completions API, sending the message with the injected schema JSON, and returns a result object instead of raising an exception. Now we'll create a text variable, which is a list of strings of various inputs, and then process them to see the results. And here we see a success status for the Alpine Pro tent, a success status for the Summit backpack, and also a success status for some random text without product info because it returned the default product, price, and one attempt. Now let's jump into the last notebook and look at some more advanced prompting techniques. Once you're comfortable with basic API calls and structured outputs, the advanced techniques we'll cover here will help you get more reliable, accurate, and maintainable results. First, we'll look at few-shot prompting, which gives the model examples of the input-output patterns you want, where the input is the example user message or data you send to the model, and the output is the example response or result the model should produce. This improves consistency for custom formats or domain-specific tasks. It costs more tokens but reduces errors when zero shot falls short. Next, we'll look at chain of thought reasoning, which asks the model to show its work step by step for complex problems like math or logic. This improves accuracy on multi-step tasks, but adds latency and tokens, so you'll use it strategically. And finally, we'll look at prompt chaining and decomposition, which breaks complex tasks into multiple focused API calls like extract then respond instead of one overloaded prompt. Each stage has one job, you get structured data between stages, and the whole pipeline is easier to debug and maintain. So in zero-shot prompting, you only give the model instructions, no examples. Few-shot means you add example inputs and outputs so the model learns the pattern. For something like sentiment classification, zero-shot often works, but for more custom formats or edge cases, few-shot is much more reliable. We'll cover both and then combine few-shot with structured output. So starting with zero-shot, we provide a system role in the content asking it to classify the sentiment of product reviews as positive, negative, or neutral. Then for the user role, we add the content of this tent is okay, nothing special, but it works. Now we'll go ahead and run this cell, and we see that the classification came back as neutral, which makes sense for this content. Now in few-shot prompting, again, we're giving the system role the same content to classify the sentiment of the product reviews as positive, negative, or neutral, but we're also providing several user roles with content for which the first example is this backpack is amazing, super comfortable, and durable. Then we tell the assistant role that the content is positive. Here we're providing a negative sentiment content, here neutral, and then the actual user role query has the content of this tent is okay, nothing special, but it works. So let's go ahead and run this. And as expected, again, we get the neutral sentiment. So few-shot works because the examples fix the output format, clarify how you want edge cases handled, and keep style consistent. But again, the trade-off is more tokens, which means more cost and latency, so use it when you need it, not everywhere. Now let's look at few-shot with structured output. So we can combine few-shot prompting with a Pydantic schema. Here we've defined a sentiment analysis class with sentiment, confidence score, and reasoning properties. Here are the example input-output pairs, which we concatenate into the samples text variable. Then we include the sentiment analysis schema in the system prompt with the examples and the user roles content in the same format as the example structured format. So this gives us both pattern priming and validated JSON. Now let's run it and see the results. And here we see the sentiment is neutral. It's 87% confident. And the reasoning is that the review expresses a lack of strong opinion, indicating functionality without enthusiasm. So when it comes to zero-shot and few-shot prompting, use zero-shot for well-known tasks like summarization or translation, and use few-shot when you have custom formats, domain-specific terms, or tricky edge cases. Just remember the token trade-off. Now let's look at chain of thought reasoning. So for multi-step problems like a word problem with discount and a gift card, you can ask the model to think step by step. That often improves the accuracy but adds length and latency. In this first example, we'll ask the model to perform a math question with no reasoning instructions. So let's run it and see the results. And we get a direct answer of $250. Now, with chain of thought reasoning, we'll instruct the model to solve the problem step by step. And if we run this, we see the chain of thought reasoning that the model went through to solve the problem. Before we move forward, I just want to point out that when using chain of thought prompting, the model produced the correct answer. However, without it, the result was incorrect, which is kind of interesting. Structured chain of thought uses a pedantic model for steps and final answers, so we get both the reasoning and parsable result. So let's run this cell, and we see the structured reasoning response. Now, for a prompt like classify this statement, asking for step-by-step reasoning is obviously overkill. It's slower and adds more tokens. Here, we'll run the same simple classification with and without a think step-by-step instruction and compare time and length. So here we'll run it with reasoning, and here we'll run it without. So let's run the cell. And we see the comparison with reasoning, 3.14 seconds with 672 characters, and without reasoning, 1.53 seconds with 8 characters. So again, use chain of thought for complex reasoning, not for every task. Now, when a task mixes multiple goals or outputs, a single prompt often gets messy and brittle. Chaining lets you split the work into smaller calls with clear inputs and outputs, which makes the flow easier to debug and extend. A single overloaded prompt is hard to control and hard to parse. Breaking the task into multiple focus prompts with structured data between them produces more reliable and maintainable systems. One big prompt that does extraction, classification, and response generation is hard to control and hard to parse. It's better to break it into stages. First, extract the structured data, then generate a response from that data. Each stage has one job, and you get structured data in between. In the next demos, we'll show the overloaded single prompt, then the chained version with 2 API calls, and finally a small pipeline function that does the extract and respond. So looking at this single overloaded prompt, we see it asks for extraction, sentiment, issues, and support response in one go. If we run it, we see unstructured output that's hard to use in code. Now let's look at this chained prompt example, where stage 1 extracts product name, sentiment, and issues into a pedantic model. Stage 2 passes that structured data into a second call that writes the support response. It's the same input, but we get clean data in a focused response. Now let's wrap this up with a function to extract, set priority from the analysis, then generate the response with that priority in the system message. And when we run this, we see the full result: analysis, priority, and response. So that concludes this video on prompt engineering. If you found it useful, feel free to give it a like. And if you'd like to be notified when I add more content to the channel, please consider subscribing. In the next video, we'll explore retrieval augmented generation, or RAG, which gives your LLM access to external knowledge so it can ground answers in real data. Thanks for watching.